All right, so like I said, today's learning target is all about graphing absolute value functions, and we're going to try to graph it without the calculator, but I will show you how to plug this into the calculator as well. So looking at our first warm-up question here, I'm going to just write out, for a function, we kind of have this form that we've been seeing over and over, right? It has the A, the H, and the K. And we will see it in this unit, and we will also see it in next unit. So what does the A tell me when I look at this function?
Stretch or compress.
Stretch or compress, perfect. What else?
Reflect over x-axis.
Yep, whether or not I reflect. What does the H tell us?
Transform left or right.
Translate, left, right. Sorry, just to make sure we use our big terms. It is a transformation, though. And then the K,
translate up or down.
Up or down. So those are kind of important things to know, because today the only difference is instead of these being parentheses, they are going to be absolute value bars. So this is what I mean, how functions have a lot of connections regardless of the type of function that you're looking at. So today, as we look at functions, we're going to evaluate what the A value is, and it's going to tell us if the function is facing up or down. We're going to look at the H and K to figure out where the vertex has been translated to. Has it moved left, right, up, or down? So let's get started, though, and make sure that we know what an absolute value function looks like, because you've probably never studied it or really had to graph it before now. We know that absolute value is the distance to 0, and we're just going to be graphing y equals the absolute value of x. This is what's called like a parent function, right? We start with something like this, and then we're going to move it all around the coordinate plane. So let's do it just kind of like we would if we were in Algebra 1. I'm going to make a table of x values. So let's do our kind of standard -2 to +2. And let's figure out what our y values are for each of those. So if I take the absolute value of -2, I get 2. Absolute value of -1, 1. Absolute value of 0 is still just 0. Absolute value of 1 is 1. Absolute value of 2 is 2. So now I have a collection of coordinate points that I can graph right here and connect the dots to draw my function. So I got -2, 2. And obviously, this doesn't represent all of the points for my absolute value function, but I'm hoping we can see if we kept adding more numbers. Kind of okay. Let me see if I can draw it a little bit better. Here we go. That is my absolute value function. So what type of shape does it have?
Probable. Or V.
It's a V. So if I'm studying x squared, I do have a U shape. I have a parabola shape. When I study absolute value functions, you will wind up with a V shape. So if you don't have a V shape, we've done something wrong. What is the vertex of this function?
X origin.
The origin, exactly that. Right? And when we talk about vertex, it could either be a minimum or it could be a maximum. It's when your slope changes. So in this case, I have a negative slope, and then it changes to be a positive slope. So wherever that change happens, that's what we call your vertex. It could be a min or max. In this case, is it a minimum or a maximum?
Minimum.
It's a minimum. So last unit, we talked about the fact that a transformation changes a graph size, shape, position, or orientation, right? Last unit, we had a whole section over it. And a translation is when we shift a graph horizontally or vertically, but we don't actually change the shape of the function. And I just wanted us to kind of refresh these because it's really easy to mix them up, right? On some of our tests, I saw that we would use the word transform when we meant translate. Totally fine, just wanted to make sure we redefine these because we'll be doing this again now. So let's look at our parent function, but all I've done is I've thrown in that a, h, and k again that we're used to. So the graph has a vertex at the coordinate point. Remember, I'm going to take the opposite of what's in here, because inside the parentheses it was opposite of what we thought, so my vertex is at the coordinate point hk. The graph is going to be V-shaped, and it's going to be up, like the right side up V, if A is positive. So however you want to write it in your notes, if A is positive, A is greater than 0, whatever makes the most sense to you. And it's going to be an upside down V, or facing down, if A is less than 0, or a negative number. So before we would talk about how the graphs before, right, would be reflected in the x-axis. Well, now that's just going to really tell us what our orientation is. Is it up or is it down? We don't necessarily have to explain it as a reflection. The graph is going to be vertically stretched, meaning, right, this graph has a nice slope. What is the slope of this absolute value function? 1, right? It's 1 this way or negative 1 this way. We're just going to call it a slope of 1, positive or negative. We're not going to focus necessarily on the positive or negative slope. I'm going to stretch the graph if the absolute value of A is greater than 0. Sorry, greater than 1. Greater than 1. Just copying, moving ahead. Greater than 1. Right? If my A value is 2 or 3 or 4, that means that my slope is 2 or 3 or 4. Then the letter A is going to tell you exactly what your slope is. The function is going to be kind of vertically compressed or pushed down closer to the x-axis if the absolute value of A is less than 1. So something like a fraction, for example. If A was equal to 1/3, right, that's a number that's less than 1, and that would mean I've pushed the graph down closer to the x-axis. So let's look at an example absolute value function. And we've got a negative sign out front. So does that mean it opens up or opens down?
Down.
Opens down. So instead of saying reflect, we're just going to say we have an upside down V, right? It's going to look like that. And then the A value is a 2, which means we've stretched it, right? Stretched by 2. And the way that we interpret this so that we can graph it, it means my slope is going to be positive and negative 2, right? Since I have a V shape, one of my slopes has to be positive and one of my slopes has to be negative. Right here, the +2 tells you how have I translated the graph from my parent function of just y equals the absolute value of x. Have I gone right or left?
Right.
So remember, it's the opposite of what you think. So a +2 sends you to the left. This -1 tacked on the end tells you that you translated down 1. So if I started at the origin and I now have moved left 2 and down 1, what is the coordinate point of my vertex? Well, left 2, -2, down 1, -1. So -2, -1. Do you kind of see that connection, right, between I can just look at the function here and say, I'm going to take the opposite of the number that's with the x, that will give me my x coordinate, and I'm going to take the k value, that will be the y value of my vertex. So now that we kind of have a map about how absolute value functions work, we're going to start graphing them, which is our learning target. So on the next page, we have our first example, y equals 2 times the absolute value of x plus 1 minus 4. So here's kind of how I like to do it. First, I like to write down, does it open up or open down?
Up.
Yep, opens up. What is going to be the slope of it? Positive negative 2. I just look at the a value or the number right in front of the absolute value bars. And then looking at that, what is my vertex? I take the opposite of the x, Kevin.
-1, -4.
-1, -4. Now your notes ask you for the x-intercepts, but we won't know the x-intercepts till we graph it. So let's graph it and see if we can clearly see what the x-intercepts are. So I graph -1, -4. So that is my vertex, and since it opens up, that's going to be my minimum value. I then use the slope from the vertex to go up 2 to the right 1, and I'm going to do that so I get enough points to draw it well. But then I also have to draw the other half of it, which will be up 2 to the left 1. Finally, connect the dots. There we go. So what are my x-intercepts? My zeros. Peyton?
-3.
Yep. And?
1.
Yep. So sometimes you'll have to look at the graph to be able to pull information out like that if I were to ask you for additional information. Okay. Let's look at the next example. Does it open up or open down?
Down.
Opens down. And like I said, you don't have to write all this out. This is just kind of what helps me as I go through the process to make sure I don't make a mistake. What is going to be the slope?
Positive and negative 1.
Yep, positive and negative 1/2. Right? Even though it's a negative 1/2, it's going to have two sides of that V shape, which means I have to consider both positive and negative. What's my vertex?
1, 5.
1, 5. So I'm going to go ahead and plot 1, 5. And since it's opening down, I still have room on here that I can fit in a few more points. Down 1 to the right 2. And then down 1 to the left 2. Draw as many points as I can. Now you'll see for this example, I didn't ask you for the x-intercepts because can't see them on my graph, right? I didn't give us a big enough piece of graph paper. But that is kind of the crux of our learning target, graphing absolute value functions. Let's kind of go the other way. Oh, sorry,
Do
question.
you think we could find like the x-intercepts without having to?
Yes. How would we find the x-intercepts? What is the y coordinate? Yep.
Never mind.
Are you sure?
I'll try it.
Yeah.
Can you find find the equation and plug it in? Or okay, never mind. I don't know what
I feel like you're thinking you've got it, but it's just putting it into words. I get it. Yep.
Would you replace the f of x with 0?
Exactly, right? Look at all of my x-intercepts. They have a y value of 0. Remember, those things that we learned when we were talking about linear equations or quadratic equations, they hold true here now. X-intercepts always have a y value of 0. So I set this equal to 0 and I solved. And we know how to solve these now. So yes, I would be able to get my x-intercepts. Obviously, I normally don't teach it in this order, so that's why. But yeah, great job. All right, let's go the opposite way. What if I give you a graph and we have to figure out what the equation is? I do the exact same process. I write down all the pieces of information I need. Does this open up or open down?
Down.
What's my slope?
Positive, -2.
Yep. And then what's my vertex?
-2, 2.
-2, 2. Oh, I chose way too many 2's. Sorry about that. So let's write our function. So it opens down, so it's going to start with a negative. Then it has a slope of 2. I really did pick too many 2's. Then I have my absolute value bars. And I'm going to take the opposite of the x-coordinate, so x plus 2. And then I have to tack on the extra, plus 2, in the end. Want to try the next one on your own? Yep, go ahead, give the next one a try on your own. We're pretty ready. All right, so it opens up. My slope is positive negative 1/3. Remember, when you're finding your slope, just make sure you find where it really crosses the grid lines, right? Don't try to estimate. Find where the line crosses the grid lines. And then my vertex is at -1, -2. So my function opens up, so it's going to have a positive slope of 1/3. Then I have my absolute value bars. Take the opposite of my x-coordinate, and then tack on the y-coordinate at the end. Not too bad, huh? You have a question back there? No? We're good?
No,
Okay.
I got it.
All right, so let's jump into our one-word problem for the day. Try to spread out our word problems. So at a science museum exhibit, a beam of light originates at a point 10 feet off the floor. It is reflected off a mirror on the floor that is 15 feet from the wall the light originates from. How high off the floor on the opposite wall does the light hit if the other wall is 8.5 feet from the mirror? All right, so obviously this is a word problem using absolute value functions. I mean, it is true, at museums they can't really direct light directly on art and stuff. So they do have to use different ways of lighting museums. Whether or not they use an intricate mirror system, I don't know. But as you can see, we do have a V-shaped function. So because we have a V-shaped function, we will model it with an equation using absolute value. So let's talk about what we do know. So let's think. Anybody have a point that exists right now in our function? Like a coordinate point. I would say, let's imagine, right, this is my x, this is my y, and this is my origin. So we're moving from there. Yep.
0, 10.
0, 10, yep. That's on my function. What's another point on my function, Kevin?
0, 5, B1.
0, 5, like right here?
Or no, sorry. Like at the end. I'm trying to think of what.
So this point here?
Yeah.
That's the point we're trying to find.
Oh.
We don't know. Well, I guess, right, we can say that we do know. What's the x-coordinate here? 23.5. What we don't know is the y-coordinate. That's what we're trying to find. We're trying to figure out how high the artwork is. Carter?
15, 0.
15, 0, yes. And we're going to need that point because which one of those is my vertex?
15, 0.
This one is my vertex, which we know is going to be really important for writing that equation that we're going to need. What's my slope? do need the slope, right, to be able to, yep, you got it, Kevin?
2/3.
Yes. Positive, negative, 2/3. How'd you get that?
I did 10 divided, or 10, I did 10 over 15 and then I just
You
reduced.
simplified it. Perfect. So because, right, I don't have all of the information, I don't have a big coordinate grid, I can't count, but I can go down 10 to the right 15. That represents my slope. Now I feel like we have all the information we need to be able to write this function, because we have to plug in 23 and a half for x and see what we get out for our y value. So let's write our function. You can use f of x or y, really don't care at this point. Does it open up or open down? We're going to fill that in. It opens up, so I need to make sure it starts out as a positive number. So I have 2/3, because that's my slope. And then I'm going to take the opposite of my x-coordinate. And if you want to, you can put a placeholder of +0 at the end, but you don't necessarily have to. So now, in order to be able to figure out how high this is off of the floor, I just plug in 23.5 for my x value. And I don't know, why don't we round to 2 decimal places? Get a little approximation here. Or is it a nice, let me see, I'm guessing it's a 2/3 number? Does that look right? I got 5 2/3 feet. Or 5.67 if you'd rather write it as a decimal. Right? Because when I'm evaluating this, I treat those absolute value bars almost as if they were parentheses. So I've got to evaluate what's inside here first. I get my 8.5 out. And then I take the absolute value of 8.5, which is still just 8.5, and then I multiply it by 2/3 to get out my answer. Questions?
I forgot, how do you turn something into a fraction on the calculator?
Math, enter. We'll turn it back into a fraction. I think by default, or at least on these calculators, the black calculators, you might be able to see a mixed number, but I think it's usually an improper fraction. But yeah. So here's how, this is just a little aside because we're done with our notes for the day. If you do want to put this into your graphing calculator, I want to make sure that we know how, right? I'm always about showing multiple representations. So when you go to your y equals, you just have to grab that absolute value function. So that's under the math button. And then the num category for number, you would grab your first one and then just put in x. So if we just wanted to grab the parent function, right, y equals the absolute value of x, and then hit graph, we would see our v function. So if you do want to get a visual, trying to figure out how it's been transformed, this is always an option
How did
too.
you get the absence thing at the beginning?
Math, num category,
Okay.
and then it's the very first one. All right, what I'd like you to do at this point is take out your iExcel. We're gonna do some practice on iExcel.